Welcome everyone to the second day of the open source event here in Zug. Today we start with Harald, well known for the good and the bad jokes. Stage is yours. Thank you for joining us.
Once. So, quick introduction myself. So who am I? I'm principal key expert in digital industries in Siemens. And my working area currently is communication in virtual environments, especially the container systems, but also VMs and nowadays real-time aspects. And in order to do this somehow, hopefully successfully, I had to learn also more about the underlying technology, and then you end up in OT security also. So that's my background. Open source projects, I'm also contributing upstream to, for instance, a Go test framework that is, I think, very prominently used by Kubernetes. So, what is Edgeshark? And you're forgiven if your mind plays something like that. No, it isn't. Maybe a user testimonial. It allows to do magic. So why would you need magic after all? Does this look somehow like your workplace experience in the past? So, and then how to solve a problem, how to get over these show gaps here and get into your working product. So you have to tap into the virtual wiring maybe, you have to tap into networking, virtual networking configuration inside your virtualization environment. And somehow trying to figure out that this makes sense and brings you to the root cause of your problem. So before, how did you do this? This glorious, beautiful amber glowing here. So shell acrobatics. It doesn't matter about the details because you might end up, such with our industrial edge ecosystem devices. Sorry, there isn't any shell for you either. So how to deal with that? That's the reason why we made Edgeshark. So you get all in a very nice single place, get it into context. And now for the fun part. Let me see if it crashes and burns. So what you do is deploy basically the Edgeshark service or services, and then you navigate to the web URI, click refresh, and then you get an insight about how your workload actually is wired up. So this is a very simple one, not much else. But we know already from our users, for instance, from the industrial edge, there's often much more going on. And you can then drill down. Look, no, this is no Bitcoin address, so sorry, it won't help you. So get communication details, can check, does the system actually has been orchestrated in the way you thought it to be, or you can learn more about the system, start to better understand how to really work with the system with container engines. And then, of course, because there is a shark in the name, Edgeshark, and you might already guess or wait for it, you click on one of the shark fins, and this transfers you, hopefully, to a Wireshark session. This is basically a remote one. I'm connected here to all but a local VM, but in effect it's remote. So does it work after all? Well, let's see. Let's refresh and there's the traffic. So, and one of the typical use cases, especially with my background of digital industry, industrial automation, you often have legacy protocols, and they are a mixture about IP and non-IP protocols, for instance. And of course, you have documentation. when you try to write a workload container for it and it doesn't work exactly, you don't know, did I make a Docker mistake or a podman mistake? Did I make a mistake reading the documentation? Is there something not correctly documented? So you can easily drill down on the different levels. You can check everything is okay as it should. Oh, I see something in the protocol, for instance. How do you get magic? So this is something I really like about containers, it's instant magic. You curl or wget a Docker Compose file, and then you feel lucky and feed it directly into Docker Compose. We support different platforms here, basically Docker, Podman, Containerd, and other engines on Linux, on WSL2, Docker Desktop also. So now you have the service running. How do you use it? As I've just shown you, from a web browser or via a plugin that also is part of the Edgeshark repo system that connects you up to Wireshark. So basically Wireshark now gets container aware and can do live captures from containers. So this is what I showed you. Now you might ask, why? Why did we do this? And it's basically a twofold answer. One is, as I say, architect as a service, or ARS. No R. It's basically about empowering people. So we can take the tool, they can take their own pace, look through it, also learn about the system, can discover, can diagnose, can debug. And of course, this as a tool scales much better than I would ever scale. And so the journey starts with the general idea back in February of 2018, and it was rather proof of crash. But luckily, a few weeks later, we had a terminal version, no container yet, and so we saw it works. And interestingly, people started to take screenshots from the terminal, send it around saying, that is my configuration. So obviously it was something that people immediately found useful. On a side note, beginning of 2018, anyone in the audience remembering, have an idea what was going on in rocking IT at this time? I have to admit, I might have been influenced in the choice of a mascot. It was Spectre. But we are not doing this kind of observability as Spectre does, so rest assured. Ignore that, so there's an identity crisis. But packet streaming came in a year later, so you see there's some time to learn and then think about how could we do the live streaming and the packet analysis with the tool. And then Industrial Edge, and this is basically in 2020 where the name Edgeshark came in, and we kept it also because I think it's a very catchy name. And then there's a big shout out to many colleagues in the company, also Roger and his team helping me in open sourcing and going live on GitHub. So how does this even work? Shouldn't container totally prohibit this? Or as Dan Welsh says, containers do not contain. That's already a hint. Let's see in a few minutes. So I mentioned we want to tap into different information sources, container and host traffic, configurations such as inside the container DNS. We want to tap into what workload is going on, so we understand what names are there from a user perspective and developer perspective. And we want to tap into what the kernel actually executes or is doing as the real network configuration and state, and not some configuration data. And we do this in the following way. You've already seen the two names, Ghostwire and PacketFlix. So these are the two layers, the two services. So let's start with Ghostwire, the lower level, here with the discovery. So one of the standard APIs we use is, of course, Linux kernel APIs, where RT-Netlink and NFT are the new filter tables. Here, process file system. So these are the well-known and typical sources. There is no magic or no 0 day behind this here. We somehow have modularized this, so the Ghostwire service only does the communication discovery part. But for us, we need information in general, more general about what's called Linux kernel namespaces. There's the technology from which also containers are built, typically, if we don't talk about micro VMs or other architectures. So again, process file system, and in the end, reading via virtual file system functions, the usual thing. This layer talks to the different container engines we support, so Docker, container. We also support CRI with the new Event API extension. So this is both CRI-O and containerd here, and then also podman. And you can already guess, so we call them whale watchers. It's more like Tempo, a generic term. These engines then, as usual, manage all the ugly low-level details of creating the necessary kernel resources, making some sense of them, combining them. So it's basically the same. It doesn't matter if it's container or host. It's just something we, as a user or developer, what we think in user space is a container, but the kernel itself says, I don't know anything about this. I only know the small details. And this one allows us to read things like, for instance, CNI configuration, DNS configuration directly from the containers. I will show this in a minute here. And with this information here, we can finally start the captures. So this is, again, no magic, it's all well-known elements. It's dump cap from Wireshark project that is just being orchestrated and correctly attached, and then the streaming goes back. So that's the general idea, how the whole system works in general. And that brings us to the frequently asked question of, where do you mount the Docker sockets? So do we have any PSSOs in these? So I have these, these nice, sturdy brown bags here. I think our part of the audience might be glad if you take precautions here. So the reason is, or the answer is, no, we don't. And because it's magic, of course. Okay, so let's look at two example containers, Alice and Eve. Some of you might already guess what the rows are from the name, but they're just containers. They have processes. So we have a process in Eve, and a process in Alice. And so what's this container? They have their seemingly own file system, their own files. They have a process file system, and they live happily thereafter. And I think one important thing, and I learned this only very late, is, so if people talk about the technology of mount namespace and container, then we typically tend to think in, oh, that is separating, isolating, whatever you call it. So a file here in this container can't be seen anywhere else. The point is that this isn't virtual file system separation. And the architecture of Linux, and I think this is similar to other Unix-like systems, is you only have a single virtual file system, a single one. And container technology doesn't change that. That's completely different from, say, virtual machines. This is very important because you cannot just look at mount namespaces or at another property in isolation. With containers, and when it comes to security or finding useful ways to make tools, you need to look into multiple dimensions, multiple technological aspects of containers. And in this case, we need to look at how are the processes here actually organized. So for Alice, that's what we typically read everywhere. So we have the process and it is contained in its own so-called child process identifier namespace. But for Eve, we do differently. We use the parent PID namespace, that's the one of the host itself. So why should this matter at all? Because if we look here, Eve has its own process file system, its own files. There's a problem here. Wormholes. There's a very useful pseudo element called root in the process file system for each and every process and task. I have to admit it took me years to understand what this thing really is good at. And what it does, as illustrated here, it gives you the view into what other processes are seeing. And as Eve is now being able to see processes from Alice, it is able to see the files as seen by Alice. So you get access into our containers, into the file system. You don't need any shenanigans. You just need to construct the right file path, and then you can immediately read, write, whatever you want, normal file system operations. And this is something actually that is very well known for a sufficient definition of well known. So tools like CAdvisor, but also the BCC tools use this. When we unwind the stack, load the symbol tables from the shared libraries, I noticed they use exactly the same thing, independent of containers and of this use case. It was also a surprise for me a few weeks ago. So why should this be helpful for us? Because we want to tap into the container contents, DNS configuration, or maybe reading other things that might be necessary also. And the other things is, how do we basically talk to the API endpoint of container engines when I'm in a container and the engine is in the host? Or might be even in a different container. So basic strategy here is we first scan the process tree or the process list, and we look for well-known names. So of course, this is not a forensic tool, because otherwise you would need to do much more comprehensive scans, for instance, doing checksums, hashes, and v1. That's not the purpose here. This is a quick discovery service on the basis is we are all good friends here in your host. So we scanned for a well-known process file. for process names. And if we find them, we scan for their open Unix domain listening sockets, so potential API endpoints. There is no hard coding about what the endpoint names of a different engines is. It's just looking, oh, you have a set of open Unix domain sockets in listening mode, looks like an API endpoint. Just construct the proper path, so from my container via my process file system out into a different container of a host where the API endpoint is, and bingo, presto, business as usual. Yeah, but there's one fly in the ointment I have to mention here, podman, or detecting the undetectable. So a design feature of podman is that it is typically deployed as a service that it starts when someone connects to the API endpoint, but terminates thereafter if all clients have disconnected and the service is not needed anymore. Now there's a problem because we can't rely on this situation. On a side note, this looks great, running a container engine only when strictly needed. So the point is, what is strictly needed? So there are use cases where you don't need the engine, but in many other cases, you need to do diagnosis, you need to do telemetry, you monitor your workload. How do you do it? You do it via the container engine because that is supplying the telemetry data. So whenever you do this, something real workload, either is developing or deploying, you need the container engine all the time anyway. So this is really making it more difficult for us, but anyway, so the solution how we deal with a situation or work around it is we now do not try to detect the engine directly, but instead we look, is there a system manager? And that's basically nowadays systemd. Okay, of course, in an interactive system, client station, you have at least typically two instances, one for the system itself, one for the user. We then scan, and in this case, we need to know at least the final part of the API endpoint names. If we find them, that's good. We connect to it. It's a little bit more complicated in our case because we need to know the engine PIDs later to do translations in the system. But anyway, and then we can proceed, as I've shown you before, with the other container engines. So we have a workaround for this. It works, but it's not something really to be proud of, to be honest. But anyway, so with that, let's sum up. Of course, Edgeshark, as the name suggests, it's tapping into the traffic of container hosts, of containers. And this is not downloading because we're in the age of streaming. And you stream your video, you don't drive downtown and rent a VHS cassette, for instance. So streaming is the way to do, but it's much more. And so Edgeshark is also more than just a web UI to start Wireshark. It taps into the virtual network topology. So depending on your system setup, that might be more complex than expected, or it might be very stock simple one. So it depends, but even then it has, and I've seen this many times, people getting help from me, asking for help, problems with their containers not working properly, and then this is something to show them, okay, this is how your system really looks like with all the other applications and your application. We tap also into the information about open and connected ports as well as forwarding. So one part is basically a netstat on steroids because it is now container aware. So you get the detail, not only, okay, there is a port open, but and maybe a process, and then you end up with all the containers having initial processes called shell. That doesn't really help. So what we show is which container really, and also in the case of Kubernetes, we get also via the CRI layer the information, so we know what a pod, for instance, is. So we have support for especially Docker, the port forwarding, as well as kube proxy. In principle, we have also support for CNI plugin forwarding, but that is not very well tested, and there might have been regressions. But anyway, it's an open source project, so it's a perfect way. If you notice and you need it, please send an issue and then a pull request. As you've already seen, so tapping into multiple engines, that's extensible. So as long as you have a Go client API implementation, you can plug in more. And while it's up in the behavior of the information, so we support, as I said, Docker on the higher level, Containerd, both standalone as well as part of Docker. And then, of course, as part of Kubernetes, CRI-O and podman, of course. So, as I've shown you, we have engine in container auto detection. That is very useful if you do things with KND, Kubernetes and Docker. So you only need to basically start with those on the host, and it also automatically sees your clusters and has also awareness detecting from container meter information, okay, that is a Kubernetes and Docker node, for instance. So that's the Kubernetes and Docker awareness. For things, we have an online manual. There's also an integrated tab in the web UI itself. Something that is really helpful if people phone in and say, okay, I have a problem, or send an email and say, okay, click on the camera button, send me the screenshot, and that gets automatically downloaded. And that's helping in many cases to get a first idea what the system is, what's going on, and to further help people, or for documentation people. With this, thank you very much. Maybe, of course, the link, so github.com/Siemens/Edgeshark.
Thank you for the very interesting presentation. I for sure will try Edgeshark out because we also develop embedded devices or with container runtime like the X devices. I'm wondering what is the footprint if I have to put it on the host?
Depends on what you calculate. So the container images are something like 30 meg. And runtime depends on how you want these are Go implementations. And so you can start with, for instance, 32 meg. I've even run it once for testing purposes with 20 meg. It then gets just slower because there's more garbage collection going on more often. But we are talking about, at least considered in the context of OCI containers, we are talking about 30 megabyte per service and something like between 32 and 64 megabyte for RAM in total to execute and to stream.
Yeah, thank you. And the follow-up question, so I see to let it run and deploy a compose file, more or less. Are the containers also ready for or compiled for ARM?
Yeah.
Okay, perfect.
Multi-arc support, so that was something also where I could finally learn how to do this. It's always good to have something that is in some case a toy to learn new things, as well as a useful tool for the colleagues who do the real development stuff. So for the containers, we have both 64-bit support for x86 and ARM. So it's completely transparent because these are multi-arc images. You pull just from the GitHub registry, so that is right up in the example Docker Compose file. And on the desktop side or on the client part, we support different distributions, so Alpine, Debian, Ubuntu, Fedora, and was even people asking for Arch. So we have also, that was also something completely alien and new for me. Not really my ecosystem, but anyway, of course, Windows and also macOS. And here goes a big shout out to Roman Nodin, the product line manager from Nokia. So he came and said, "Oh, could we somehow get this, what I showed you here, the one-click method also working on Apple, because that was on macOS missing." I said, "Unfortunately, I have no clue how to write Apple script and things." And so he somehow located colleagues or wherever he got his sources, and 2 hours later I had the pull request for the feature. And when I tried it on an old stale macOS book that our EKV thankfully gave me, got it working, and off we go. So that was also a very nice experience to have this kind of cooperation from outside coming. Yeah.
I would have a general question regarding your open sourcing experience. So you already mentioned this Nokia contribution. So how much did you get back from the open source in this last year, I think, since the publication, and how much extra time did you invest into the community interaction?
Yeah, in the moment, so what I got is from Nokia, or from a container lab community actually, is one thing is this contribution about making it on macOS work, and some nice vessel and bills, so you see where you're connected to in the status line or title of a Wireshark app. The other one at the moment is still very isometric, so I got feature requests, which were luckily something very easily done and very well, because we had already come about the same usability issue also, and we found also very long-standing bug we missed all the time. So yeah, at the moment I did it myself, but I hope that I over time still can manage to grow a community, and basically thinking especially of yesterday's talk, stepping rather more back, and hopefully that the project will in the future carry itself at some point. So for me it is still also a tool to use myself at work. So it's also some of the features driven by our work here with our industrial edge ecosystem, with the background of the applications. So that might in the future also bring additional features, but I hope that there will be more contributors in the future show up.
Did you have a look into building the service containers reproducibly or signing the containers? And can you run that in air-gapped environments?
You got me there, because it's based on Alpine at the moment. So, and that is by definition not reproducible. So, Felix, you know, pull request. But it needs to run on GitHub.